Can you hear me okay? Great. Okay, good afternoon or good morning. It is super great to be here with all of you. I'm Rebecca Vieira, and in my day job, I work for PhET Interactive Simulations out of the University of Colorado Boulder. Um, and I'm based in Washington, D.C., so I do work remotely because my work is mostly global. But in my previous life, I was a high school physics teacher. I taught in the great state of Illinois in the public schools there. And I guess the reason I got kind of into this whole
Oh, you cut out. Rebecca, you've cut out.
Did she not hear us?
No, it sounds like she can't.
We can send her a text message.
Can't hear me, Chris?
Yes, now we hear you again.
You can hear me now. Okay, sorry. Were you hearing me at the beginning or no?
At the very beginning, so you're based in Washington, D.C., and then you started
Okay.
talking about how you got into what you're doing now.
Got it. Tell you what I'm going to do. I'm going to go ahead and just use my computer audio. I'm going to disconnect my phone and I'll reconnect it just when I need to.
Sounds
Okay.
good. Yeah.
Give me 1 second to go ahead and do that. All right. Are we hearing okay?
Yes.
All right, I've just switched things over. So, yeah, what I was saying is that I used to be a high school physics teacher, and we would take students to Six Flags every year, and generally we take the entire junior class. And so, when we would go to Six Flags to an amusement park to have students go and collect like real data on the ground, we often made use of things like Vernier and Pasco. Sometimes the Illinois section of the AAPT would actually be out there and lend people vests, but I think there were like 10 or 15 vests for the thousands of students who were out there that day, and it just wasn't enough. So my husband ended up developing an app for me because he is a mobile developer by profession, and it ended up turning into something that became much more popular and used not just in high school, but at university levels. And a lot of people in research and engineering fields, and even in medicine, and of course in straight up physics as well. There's been a lot of really high quality peer reviewed journals that have made use of sensor data through our app. So that's what today is going to be all about, is just making you familiar with what is out there, with what's possible. And let me go ahead and start sharing my slides so that you can see kind of the agenda I've set up for us and see what else you might be interested in. So I was hoping to share with you just a bit about, what can you do with your smartphone? I was hoping we would actually play a little bit so we can get familiar with some of the sensors. I want to share some of the research behind the use of the Physics Toolbox and sensors more broadly in smartphones in teaching physics. We'll take a look at some scaffolded challenges. We'll take a look at how sensors work. We'll also take a break. I know it sounds like a lot. It's just a lot of different little small things. And then we'll take a look at what could an in-depth lab look like, and then look at some special features. And of course, hopefully engage in some pedagogical reflection as we go along. Just so that I make sure, Chris, am I coming through nice and clear now? Okay, good. Just stop me at any point. I was telling Chris before the recording started, every once in a while, sometimes during the midday, I just like there's 15 minutes of just weirdness. So just make some visual motions if you can't hear me or something, and I will make sure to resolve that. So kind of in summary, my personal goals for you is just to help you become more familiar with smartphone sensors, to understand what's actually going on behind those sensors so they're not just a black box, and then to think about how these might be useful in your teaching and in your students' learning. So I would love to hear from you all now. There's enough, few enough of us that I think we can just do a round robin. Feel free to share your name, what you teach, your own familiarity with smartphones, and then if you have any expectations that are different from the objectives that I came up with before I met you all, I would love to know that too, because we can totally move things around, do things differently, do some things, not others, etc. So name, what you teach, your familiarity, and expectations. I'm going to stop sharing the screen so we can all see each other. So let's see here. I think there's a way to actually force the view so that everybody sees in the same order, but I'm not sure. So I'm just going to call names. I hope that's okay. Chris, do you want to start? You're the first on my list.
Sure. Hi, everyone. I'm Chris Louie. I taught
You're
physics
muted,
at,
Chris, I think.
am I muted?
No.
No,
Okay.
no, you're not. Go ahead. Sorry.
Interesting. Okay. Hi, everyone. I'm Chris Louie. I'm based also in the Washington, D.C. area. I taught physics at a two-year college in Maryland for about 13 years, and now I run optics. I am very much unfamiliar with smartphone apps, except for the one time I attended a workshop given by Rebecca. So that's all I have to say.
Thanks. Great, Chris. Joe?
Hi, everyone. I'm Joe Hefner. I'm based in Hickory, North Carolina, just west of the, just east of the disaster area. I'm fine in my area. I taught physics for 30 years in a community college, and once in a while we did use our smartphones, but the things that Rebecca is going to show today have taken all of this to a new level. So this is going to be very cool.
Thanks, Joe. Thomas, and if people want just to quantify, you can just tell me 1 through 5 too. So 1 means I've never done anything with smartphones. A 5 means I've used smartphone apps in my classroom, specifically with sensors. So that might be helpful too. Thomas.
Hi, I'm Tom Okuma. I taught physics for 44 years, primarily at Lee College in Baytown, Texas. I'm now retired. I'm familiar with smartphones, so I'm going to say a 2.
Great. How about Anna? Anna Mersa.
Hello, are you able to hear me?
Yes.
All right. I am Anna. Located in New Jersey, about 30 minutes west of Philly. I teach at a community college, and I have used the Physics app for my online class to do some hands-on experiment.
Perfect. Awesome. Thank you, Anna. Dean Stalker.
So I'm Dean Stocker. I teach intro physics, so algebra-based and conceptual mostly, at the University of Cincinnati Blue Ash College. And I've also used Physics with my students and also had them record video and then
Dean, your sound cut out.
Yeah, it did for me too. Dean, we lost the last 5 seconds, maybe. No. Well, we'll come back if necessary. How about Gary?
Hi, I'm Gary Pager, and I'm teaching at the moment at Mercer County Community College in New Jersey. That's north of Trenton and east of Princeton. And I'm industrial physicist for mostly for 40 years, but I was also a full-time tenure track professor for a while until I discovered I couldn't raise money. And I've also been an adjunct for about 15 years at 2 or 3 places around here. And I've not used, I'm on number 1.
You're 1. All
I
right.
played around with the apps, but I haven't been able to figure out how to incorporate it into the classroom.
Got it. Thanks. Larry?
I'm Larry Weaver. I'm a full-time physics faculty at Johnson County Community College, which is suburbs of Kansas City. And I have played around with Physics, but I've never used it in my classrooms for teaching.
Great. Thank you. How about Maria?
Hi, my name is Mariella Min. I teach full-time at Monroe County Community College. That's in Monroe, Michigan. I have never done anything with smartphones, but I am trying to come up with new ideas to keep my class engaged. So I'm really looking forward to this presentation.
Great, thank you. Nancy?
Hi, I'm Nancy Beverly. I teach at Mercy College, the introductory physics, and I've taken a couple of, um, phone sensor workshops before, but I haven't actually tried them in my class, and that's the next step. I feel like I'm fairly comfortable with it, but not to the point of having directing my class to do anything yet. But that's what I'm hoping for.
Perfect. How about Pravat?
Hello, I'm from India in Chennai. I have taught physics to high school students. I still work in a school. Um, I have used Google's Science Journal, but mainly playing around for myself. I've not been able to use it in a structured way with the students yet.
Great, thank you. R. Baker?
I'm a high school teacher in Los Angeles area, and I've used the Firefox and this software a couple of times, and I've gone to a couple of workshops.
Great, thank you. Rajashree, if I said that right, let me know. Did I call on you yet? No.
Yeah, almost. It's Rajashree Babu. You can call me Miss Babu. Actually, I'm a high school physics teacher in Arizona. It's my 5th year here. I'm also from India. So, yeah, I have never used any smartphone apps in my class, but I'm really looking forward to get more ideas from this.
Great. Riju?
Hi, I'm also from India. So I've been working as middle school teacher for almost like 6 to 7 years. I haven't used smartphone in my school, but when I'm doing my college, I have used a little bit. But my knowledge of smartphone with this application might be like 1 or 2.
Okay, great. And Saga?
Hello everyone, I'm Sagar Podel. I teach physics and astronomy at Hill College. We are located south of Fort Worth. So my purpose of attending this seminar is to learn and then implement these tools for a physics lab. We are using OER lab. The vendors are so expensive, especially for the online class. It's difficult to get lab kits. They charge north of 100. So I was looking for alternative to make it affordable or if possible, free. So I'm using a lot of heat simulation in my lab. Head simulation are a nice way to play around, but that doesn't give you the sense of you are measuring something. So I was looking for that kind of possibility. And when I saw information about this seminar, I thought, okay, I was looking for this. That's why I'm here. Not for the physics class, but for the astronomical observation part, we use compass, and for general measurement, we use ruler. So that's all the things that I use phone for my classes. Other than that, I'm looking forward to learn more, and maybe I'll be able to implement some of these sensor-based measurement in my physics labs.
Great, thank you. Did I miss anybody? Doesn't look like it. Okay. All right, thank you. I appreciate taking that time because it, number one, helps me to just get a sense of like all your level of familiarity, and I think it's always just nice to know where people are too, because you might find people are your resources to each other. And we're all across the United States and from all different places, which I think is so great. The first thing I want to mention is many of you have mentioned multiple types of resources, and I think that is fabulous. Especially, so I will say we are good friends with Phyfox. Phyfox is developed out of Aachen University in Germany. by somebody named Sebastian and his team, and they are wonderful, and they are active members of the AAPT, or at least they have been in the past, pre-COVID. And their app is a little bit different. They take a slightly different pedagogical approach. I think they're complementary, and I think that as teachers, we always should use many resources to fit things in different ways. Same as what Sagar was just saying here about like using PhET simulations. Obviously, I work for PhET, and so I love PhET simulations, but I would never tell somebody just do everything online, right? Or hands-on is always better. That's not always true. Sometimes you want both things. Sometimes one is actually better than the other. So I know this is all about Physics Toolbox, and I hope that what we've produced is helpful. But these kinds of like explorations we're going to deal with in the sensors, you can find on many different kinds of apps. So we will talk about and use Physics Toolbox, but don't let that deter you from using other things too. So I want to share just a couple other things before we get started. So I believe Chris included in her email a recommendation about some additional things to bring today. And if you don't have these things, they're not super critical from the standpoint of, you may not be able to do the specific activity, but these are small things. But in terms of if you want to be able to do a lot of stuff with your cell phone, these are the most critical or the most useful things, I would say, for certain studies. So one of them is the use of these ceramic magnets. Did anybody bring ceramic magnets today? Anybody? I mean, I'm always happy to just demo things, but if you do have ceramic magnets, it would be good to have them for the next hour or so. These are different from your traditional, let's say, thin, flat refrigerator magnets. These magnets are super duper cheap. You can get them from any hardware store basically. They also won't like pinch the student's fingers or anything like that, so they're not as strong as neodymium magnets, but I strongly recommend that you have those. The other thing that I suggested that you have is a Ziploc bag or some kind of a large food container that is airtight that you can actually fit your phone into. And then the other thing that I encourage you to have is a ruler. Beyond those things, pretty much when it comes to Physics Toolbox Sensor Suite, we try to make everything accessible without having any other resources. Even things like magnets, you can probably find magnets in your environment or something that's magnetic. If you've got a speaker, earbuds, things like that, they may not be quite strong enough for what we need to do, but you can always go and find something at some point. And I would also encourage you as we go throughout, I don't know if we're going to get to a point where you're going to need to or want to do that, but your phone is able to screen share through Zoom as well. So if you come to a point during this workshop where you want to show us what's going on your phone, you can actually take your phone, go to the, whatever the email invite is that you got, click on it, and you should be able to access Zoom and then screen share. I'm going to be doing that a little bit with my own phone as well, because otherwise it's really hard, to be honest, to facilitate like a workshop or to facilitate online teaching, if any of you are still doing that, without like actually showing what's happening on the phone. Let's see here. And then I would strongly encourage you, just keep yourself on mute when you're not speaking, but at any time you want to speak, just unmute yourself because we're a small enough group. And then I strongly encourage you to have your camera on if possible, just to encourage collegiality and discussion. But of course, we're all adults. There are times when you have to step away. There's times when you don't want to be on camera. That's totally understandable. It's just something that I encourage. And lastly, you need to get out of your chair and do stuff with me. So don't be afraid to step away from the computer with your phone when we're doing activities. We don't always have to see what's going on. It's more important to me that you're engaging so that you can come back and have conversations with us. So I know Chris also asked you to already have downloaded Physics Toolbox. And if you haven't, then hopefully you have a smartphone, and hopefully if you go to, oops, wrong thing, Physics Toolbox, from your phone, if you're using an Android or an Apple, either one, you should be able to get to that and to download it. I'm going to go ahead and give people just about 2 or 3 minutes. If you haven't already downloaded Physics Toolbox Sensor Suite, I'd like you to do that. If you have downloaded Physics Toolbox Sensor Suite, I would like you to take a moment and find out what kind of sensors does your device have. You can find that out by looking at the menu and seeing if there are any sensors that are missing. If you click on things, it will tell you your device is not compatible, and that has to do with the hardware in your phone. So let's go ahead and take just a couple of minutes to do that, and I'm going to hook up my own phone as well so that we can see what's going on. All right, so give me just a couple minutes here, and I'll get my phone hooked up.
Recording in progress.
Sorry about that.
You know, I'm going to mention, this is probably a good time. I've noticed that the free version is frustrating to use. And I pointed up the $3 and I bought the pro version, and it's a lot easier. So if people are having trouble with the free version,
Thank you for that shout out. I would say the only difference between the pro and the non-pro version though actually has to do with some engineering features. It shouldn't have any functionality difference for any of the things we're going to do today. So if you are experiencing any troubles, definitely let me know. You know, it's always possible there's a bug in one and not a bug in the other, but yeah, let's see here. Sorry, one second. I'm just going to turn this around and I am going to screen share. Actually, I'll go ahead and turn off the video and share screen. Oh. So yeah, on that point, and I didn't mean to make it into any kind of commercial advertisement. I am going to go into the pro version, but you do not need the pro version for this. So the Physics Toolbox Sensor Suite regular is has got everything we're going to do today. And are people still hearing me clearly? Yep. Okay, good. I would love to see a thumbs up, either real or virtual, if you have the app on your phone. I see Tom, Chris, Joe, Riju, Nancy, Cigar, Dean, awesome, Larry. And if people have any questions or issues, let me know.
Rebecca, Dean has a question in the chat.
Oh, I see. About magnets?
Yes. Could you address that,
yeah.
please?
Oh, I would be happy to address that. So unless your smartphone is running on floppy disks from the 1990s, the only way you're going to break your phone with a magnet is if you drop the magnets on the phone screen. I know most of us do not want to believe that because it feels so counterintuitive to what we were taught. But there is no way, and I totally get it, because I mean, I was a child of the 90s, so I totally get it. But we're not using the same technology in order to capture memory and whatnot. So a couple of things can happen when you bring a magnet close to a phone. Sometimes the screen will turn off, but that has to do with a magnetometer inside on the side of your phone, which is meant to turn off the screen when you have a like a cover on your phone that has a magnet, and it turns the screen off to save power. So that's not destroying your phone. The other thing that might happen is there's a possibility you could magnetize the frame of your phone, but that can typically be, you can demagnetize it just by laying your phone around, not in orientation with the Earth's magnetic field. And generally, you're not going to have a strong enough magnet for that to be an issue. The ceramic magnets we're using today will not cause any issue, like I said, unless you drop them from a pretty high height onto the screen. Okay, I would love to hear from folks. What kinds of sensors have we got in here? You'll see that there's a whole bunch of different stuff on the menu, but they don't necessarily tell us explicitly what the sensors are. Does anybody know what we've got in here? What can we measure with our smartphones? What kind of a sensor do those things require? Feel free to come off the microphone. Hint, hint, that's one right there. All of our acoustics data is coming from the microphone. So there's a heck of a lot you can do in there. When it comes to things like kinematics, does anybody know the name of that sensor or what kind of a sensor can measure G-force?
Accelerometer.
Yep. So an accelerometer, one accelerometer will give us G-force and linear acceleration. 2 accelerometers will give us gyroscope. And actually a single accelerometer will also give us an inclinometer and a protractor as well. We've got light. And for light, your cell phone has a whole bunch of different sensors, actually. You've got a front-facing camera and a back-facing camera. Those are not good for quantifying light. Those are, good for taking pictures, but they're still light sensors nonetheless. And then you have generally a white light sensor and an RGB sensor, red, blue, green sensor. And then we've also, on some phones, not all, have a proximeter. And that proximeter actually is an infrared sensor because it sends out an infrared light to see if there's something nearby, and it looks for infrared reflection. And then for magnetism, we've got a magnetometer. We've got some phones have a barometer, et cetera, et cetera. I just want to give you like literally 3 minutes to click on any of these things that you want to click on. And I just want you to come up with what's 1 or 2 things that you notice or that you wonder. Or if you don't have the capacity for some of these things on your phone, share that too, because not all phones are compatible. So let's go ahead and take 2 minutes, 3 minutes. Look at your phones. What do you notice? What do you wonder? Ooh, Larry's got a great question. Where is the proximeter on my phone? Now, I think mine's actually not compatible. Let's see. Oh, mine is compatible. And if you happen to be looking at my camera feed, which is not being highlighted, you'll see I'm moving my hand over the phone. So I'll come back to Larry and see if you can find out where is your proximeter sensor on your phone. Because I bet you can figure it out with your hand.
Nothing happens no matter where I put my hand. Oh, wait a minute. No, nothing. I don't get. It says no object near proximity sensor, but nothing seems to change that statement.
Yeah, I have the same.
Larry, what kind of a phone do you have?
What is this? This is a
Is it an iPhone or an Android?
oh, it's an Android.
It's an Android. So I guess one question I'd have is when your screen is turned on, do you have a little circle for where the camera sensors are, or do you not? And the reason I ask is because it is possible that if you have like an overlay screen, a screen that actually goes over the sensor, sometimes the proximity sensor will not work for this purpose. So that is one case where it may actually be there, but it may not be working for this purpose, if that makes sense.
Yeah, I can't. Where is it in the list? I've lost it in the list.
It is under, it's
There it is. I got it. Okay.
It's under
Oh,
lights.
oh, I see.
Mm-hmm.
Oh, it's in the front. Oh, okay. The one place I didn't put my hand.
The one person up at the top in the front. Yep. So almost all the sensors will be on the top part of a smartphone. If you ever get the chance to take like an old phone apart, and that's a great activity to do with kids, you can just literally pop off like the frame. You'll see that almost everything is up in that top part, right around where the camera is. All the chips are all right there. So I noticed some people don't have a proximeter. Joe, it should work even with your screen protector, I believe. What other kinds of things have we got going on there? What other questions or noticings do we have besides the proximeter?
Yeah, I have
Okay.
a question.
Yeah, go ahead, Gary.
I tried this stroboscope app and it doesn't, is it supposed to produce a sound? Or
No, this
flash
is
my,
this
oh,
is
okay, it's
supposed to
flashing my,
it's a
yes.
flashlight. It's literally it's a stroboscope for light. Yes.
Yeah,
Mhm.
yeah, I guess last night when I was playing with it, I didn't notice. I got it.
Yep, you got it. Great. What sensor in the phone does the barometer use? Great question. So the barometer itself is a sensor that's giving the environmental pressure. So can anybody think about why a phone might want to know about the environmental atmospheric pressure? What information could that reveal to a regular, not necessarily physicist user?
Whether it's going to rain or something like that.
Yeah,
Altitude?
it could potentially give you information about weather. I will say I don't think most phones do that, but I mean, it is possible. It's more likely altitude. So if you are geocaching and or you're hiking and you know you need to be at a certain altitude, that's what it's probably going to be for. Awesome. So I know most of you probably have already, I'm guessing many of you have already explored some of the more common things. So G-force, you'll take a look at. G-force is basically, I guess I'd consider it normalized, right? So my phone right now is at an angle. Typically, you would have either your X, Y, or Z component reading a value of 1 if it's, either perpendicular or flat or whatnot. Whereas linear accelerometer is giving you like the actual acceleration. So if I drop this thing, it should read a number that we're pretty familiar with. We won't do that right now. We will shortly. We also have things like simple sound meter, which is should be giving me sound intensity. Interesting that it's not actually doing that right now for me. Let me take a look. Reset that.
Mine's recording fine.
Yours recording fine. Yeah, I don't know. Maybe mine's got a bug on it. That's kind of unusual. Looks like my husband updated something on mine and it may not be great. Let me see if my oscilloscope works. Oh, my oscilloscope's not working either. I've got some kind of a strange bug. I'm sorry about that. That's kind of embarrassing. But we also have things like color detector, and I can choose, a particular color, and it's telling me, or it should tell me, there we go, what that hex value is, et cetera, et cetera. So that's just kind of like a fancy tool, probably not something I'd use a whole heck of a lot in physics. I have seen chemistry people do things like determine the relationship between the color values and the concentration of, let's say, like, a ferric solution, like is it ferrous sulfate with, blue stuff and whatnot. So all different kinds of things. What I'd like us to go ahead and do now, I'm going to go ahead and share my screen. And we're going to go ahead and do a little bit of playing in a moment here. So what I'm going to have you do is, and are you all seeing my big screen with the slides now? No? Okay, I need to probably remove the focus from my other phone. Hold on. Give me 1 second.
Does this app use a lot of battery?
I would say generally no. I mean, people have run it for hours and hours. Let's see here. Later. Sorry, I have just changed the spotlight. No, I will say if the screen turns off, the app will not collect any data. So if people are going to run it for, let's say, like an hour or multiple hours, maybe you're looking at changes in light intensity throughout the day or something, we encourage people to have it like hooked up to, to a plug or something. But no, it really, and it doesn't connect to the internet. So it's not like you're pulling down data or anything. So what I'd like you to do right now is go to the menu, game, and at the bottom, you're going to see something called play. And play is something that we've developed through the American Physical Society to get the general public engaged in using sensors by completing some super simple challenges. Or I say they're simple because they don't need a lot, but even so, they can be a little bit tricky. I will also say iPhones do not have access to light sensor data. So there's some features that your phone may not have available in that play challenge. And as you play, I'd like you to think about what opportunities or benefits do you see for using smartphones in physics class? What challenges, disadvantages are you already thinking about? So let me see here. Let me go back to spotlighting my other thing right here. Chris, can you spotlight my phone, please? Do you know how to do that?
I am trying to do that.
Let's see here. I may be able to get it.
Follow host via height. It is not letting me.
Are you all able to see the screen on my phone though, or no?
Yes.
Yes.
Yes. Okay. Yeah. All right. So you're going to go down here. You're going to click on play. And if you have lots of capabilities on your phone, you've got a whole bunch of different sensor options. Like I said, if you have an iPhone, I think that you're not able to do the light meter challenge, and it will tell you that. Do you all have at least 5 options?
I
Give me
only
thumbs
have
up if
3.
you only got 3? Okay, do the ones that you can. And I'm going to go ahead and play some music and give you about maybe 5 minutes or thereabouts to just try and see what you get. Does that work?
Yes.
Okay, feel free to step away from your computers, please. Do not stay stuck. All right? Okay. All right, I will talk to you all in 5 minutes. Try those challenges. So Dean is trying to do the barometer. Let me see if I can get that to work. And let me try screen sharing so that we can actually observe this. Thank you for your patience, everybody. It is not an easy task going back and forth between devices. And actually, I do not want to do that. I want to do video. Start video. There we go. Okay. And can you spotlight that? Or I think it is being spotlighted, isn't it? You can all see it. Can you spotlight my the screen that I'm talking with, Chris? Have we got that?
Oh, I went back to you.
Yeah, so I want the one that's showing my phone, Chris.
Oh, I'm sorry. Wrong one.
Sorry. There we go. Okay, so here I am. I'm going to go ahead and go into Physics Toolbox Play. I'm going to go into Barometer. Did anybody have success with the barometer, by the way? Did anybody get past this challenge? No. So one of the things I first have students do is to note how in the world can we change the barometric pressure without any other materials? Did anybody figure that out?
By changing the height.
Yeah, changing the height. So obviously you're not gonna be able to see me do that very well, but I can lift it up and I can lower it and it changes by, I think something like 0.01 hectopascals. It changes a very, very, very small amount. But if you were to go up and down stairs or run up a hill or walk up a hill or take an elevator in the school building, you will see noticeable difference and you can get some pretty cool information from that. So I'm going to go ahead and take it to the challenge part. And yes, some of you are saying you might need to enable permissions. That is true. So what I'm going to do here is I want to increase the pressure on the phone, the environmental pressure on the phone by at least 5 hectopascals for 5 seconds. So I'm going to place it inside of a Ziploc bag. And now some people just seal this off, but I'm going to be able to change that pressure a lot more if I fill it up with air. So I'm going to blow into this bag and try to make it a little bit more bulbous, I guess, so to speak. I'm going to zip it up because I want to be able to squeeze something, right? I'm going to fill it up most of the way. I could use a straw or just blow into a corner. Close that off pretty quickly. So now, can you all see I've got my phone? You all see it? Can you see how much
Yeah.
air I've got inside of there? I
Yes.
should be able to squeeze that. And by squeezing it, I have increased to past 139, almost 140 HPA. And you'll see that I ended up getting all the way and passing that challenge. So I'm actually able to move on. And then now there's a little simple question about checking your understanding that says, and these, of course, are questions that are really meant for the general public. If you were to climb up a mountain, what would happen to the air pressure measured by the phone? So probably something exactly opposite of what we just did, and it would decrease. So this part of the app is really meant for outreach, and we've done it with like at libraries and things like that. But I would say it is super helpful, even for the first time you're exposing your students to the app, just so they can understand all the different things that you can do. Did anybody try the magnetometer challenge?
Rebecca, before you move on,
Yeah.
your barometer is taking data much more slowly than mine. Mine is going like I'm getting like it's just going crazy.
So it could have to do with the hardware in your smartphone. So the thing is, even if I have an Android and you have an Android, it is possible that the chip is made by a completely different manufacturer with a completely different set of specifications. So some of you are asking about Pro. Pro allows you to modify those things a little bit, but probably not with, I don't believe it allows you to modify it within this game right here. If you're just talking about the barometer generally, the speed with which it collects data is going to have to do with the actual nature of the chip. So the kind of question you're asking are the questions that we often get from engineers and people who are doing research, more so than people who are using it to collect data for an educational standpoint. So in practice, it probably won't matter if your focus is just on them getting an average data point, if that makes sense. So going on to the magnetometer, I wanted to just bring this up. Who is successful with the magnetometer challenge?
I was.
You were. Who are you? Sorry, I can't see you.
Bob Baker.
Bob, awesome. So how did you accomplish this task of you had to find one magnetic object, you had to record at least 5 seconds of a magnetic field greater than 500 microteslas. How did you achieve that?
I took my ceramic magnets and I put it over the center of my left center of my phone, and that caused close to the phone.
So you could do it on the front, and this is
Yes,
a really good
left
opportunity.
on the left front of the phone, of my phone.
There we go. So this also will help you to learn where that magnetometer actually is, right?
Yeah.
And so you'll notice it is probably up in this area right here next to the camera. And you will also notice it looks like, oh, I may have maxed it out. If it ever goes to 0, for us physicists, we know that there's always a magnetic field around us caused by the Earth. It's possible that that reading is actually totally maxing out the magnetometer. You're not going to break anything, but occasionally you'll see it pause like that. So, all right, I was able to accomplish that. Now, what's super cool, let's see, the further you get away, it gets weaker. What's super cool about what you can do with a smartphone is you can also tell the direction of the magnetic field. So you can identify with a simple smartphone, is it a north, are you dealing with the north end of the pole, or are you dealing with the south end of the pole? So that's Physics Toolbox Play. And I'm sorry, I'm seeing that there are questions coming in, and I'm not able to monitor all of these questions as I'm kind of in between devices. Is there anything here that I need to address real quick? Let me remove my spotlight there. So I think, Dean, I answered your question about it locking. Awesome. Okay, it looks like most people did get past. Okay, all right. And yeah, if it worked with a fridge magnet, that is super awesome. I will say, if you've ever played with a fridge magnet, the one thing that's kind of cool, but also confusing about it for students is they don't understand where the North and the South Pole is on the magnet, because the North Pole and the South Pole are actually presented as a whole bunch of strips on the magnet. And if you actually take two magnets and rub them against each other, you'll see boop, 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 boop. And it'll basically, you'll see the attraction and the repulsion in strips, basically. For the magnetic field, north versus south, you'll be able to get the directionality of the field. And that will tell you. I'm actually not sure conventionally how it's defined.
How do you do that?
So tell you what, we're going to play with with Magnet AR a little later. Let's do it then so that we can actually visualize it together. Awesome. Okay, let me go ahead and go back to a couple of slides now that we've played with play. And as I'm talking, I'm super glad to see some people getting up and just doing stuff, because I want you to take initiative and actually do stuff. So that's great. So I do want to share real quick about what does the research say about using smartphones. And most of the research is on a variety of things, not just Physics Toolbox, not just PFOX. I know Google Science Journal was also mentioned. So these are broadly using sensors that are on mobile devices. And one thing that we know from the engineers is that many engineers are saying that smartphone, like the chips, are almost as good as the chips in the $10,000 magnetometers that geophysicists use, or that the chips are just as good as the high precision accelerometers that lots of mechanics are using to diagnose problems. And so there's quite a bit of literature in the medical field and also in the engineering field saying, if you want to do high level research, just use a smartphone with a good chip. So that's one thing. So they're pretty reliable. They're definitely precise. In terms of accuracy, sometimes you have to offset them, but generally for physics and introductory physics, whether or not your barometric pressure is off by 5 HPA is like not super duper important to getting the principles across, right? And then smartphones have been shown to really support student inquiry, primarily because it's more accessible to get the data. They've just got more access to resources to collect data. They can replace or supplement commercial hardware. Like I love Vernier and I love Pasco. I use those in the classroom too, because you don't always want your kids on their own smartphones, especially if they're not all compatible. So but even so, it certainly makes it easier for kids to do things if they have more options. And then the smartphones are super awesome for going out into the field, getting out of the classroom, going in an elevator up and down, things like that. And then we also know that smartphones can increase student interest, curiosity. There's just not much research on conceptual understanding, but and sometimes we don't see much differences compared to like using commercial hardware. But I still think that's actually a great thing, because it means that if your kids have smartphones, maybe you don't need to, maybe you don't need to use the commercial hardware if it's not accessible. Yeah, so I'll just go ahead and continue with that. So I want to show you one more way to structure activities that is not just like the play activity. That's built into the app, but more starts to look a little bit more at like physics. And again, these are all introductory pieces that I would use when I'm introducing students to smartphones. So what we're going to do, I will give you the link to this, but I'm not going to give you the link right now. We're going to just take a look at one thing together. I would first like you to go on your smartphone to linear acceleration. I hope that you all have linear acceleration. Does anybody not have it?
Do you mean linear accelerometer?
Yes, thank you. Linear accelerometer.
I don't have it. I have
You don't have it?
no gyroscope detected.
Okay. You can go ahead and use just the G-force meter. Yours is going to be offset a little bit, right? Because you're still going to get the same shape of the graph. You're going to get basically the relative normal force more than the linear accelerometer. Does everybody else have linear accelerometer? Yep. Okay, so what I'd like you to do is I would like you first to find out which way is positive X, Y, and Z, and which way is negative X, Y, and Z. So for this, you may need to do things like move around, shake your phone, shake your body. You're welcome to also drop your phone, but if you do decide to drop your phone, you don't need to drop it from a high height, and you should drop it on something big and soft, like the inside edge of a sofa or a phone. And see if you can find out for me which way is positive X, positive Y, positive Z, and they will not be the same necessarily for all of us. All iPhone users should have the same, but not necessarily Android. Because humans define the orientation of the axes, which is why it's so important we use positives, negatives, and stuff in physics, right? And if linear acceleration is hard for you to figure that out, feel free to go ahead and try to use G-force meter, because you can get some pretty easy data from the G-force meter without actually accelerating with respect to the frame of reference around you. I'm also going to show you my phone as we do this, because there's some things that one can do that I think can also make it easier to visualize this, because you may have noticed that, let me go ahead and put my smartphone up. I am screen sharing, I believe. Let me take a look. Yes. Do you all notice how you have X, Y, and Z, but you also have the total?
Yes.
So there's a way to get rid of that total and just look at X, Y, and Z. Can anybody figure out how to do that?
I went to multi and it separated it.
Take a look at the settings. So if I look at linear accelerometer, and then if I click on the cog button, you'll see that you can change, you can have show total, but you can also just look at X if you just want to look at X. So I just got that from the settings, the cog button there. So this is the X axis. And if I wanted to isolate the X axis, there's a couple things that I could do. I'm going to hold my phone, first of all, in a flat or horizontal position, like if I was setting my phone down on to the table. What would you recommend a student do to find out which way is X?
Move it right, left.
Yeah, okay, I'm going to move it right and left. There we go. So I'm definitely seeing some changes. Let me just see what happens if I jump up and down. I get a tiny bit of change, but not much. If I move it forwards and backwards, so basically towards and away from me, I have, of course, a small amount of variability, but not nearly as much as when I go left and right. So for the time being, at least, we know that the X is left and right, right? And if I change that to take a look at the Y-axis, let's see where that is. So for the Y-axis, I don't know what that old data is. If I shake left and right, I get very little going on. If I shake it towards and away from me, I get a lot of variation. And if I jump up and down, I get a little bit, probably because I'm just not jumping super great. I can't jump perfectly vertically. but it's much, much less. So that's one way that I would have students figure out what is going on with the dimensions. I'm going to go ahead and put back X, Y, X, Y, and Z again. By the way, there's also a way that you're able to visualize it in other ways. So make sure that you do play around with all the various settings, because there's a vector, there's a multi-visualization with X, Y, and Z, and then there's also the full chart visualization with however many things that I have visualized on there. So if I want to measure acceleration due to gravity, how would we do this? And I know on mine, Z is in the up down. So I'm going to stick to Z. What could I do to measure acceleration due to gravity with my phone?
Drop it.
Drop it. Okay. I'm going to take it over to my bed. And I'm sorry, you can't really, well, you can kind of see me. I'm going to go ahead and drop it. Hopefully I can hold it nice and still. Let's see what we get. Oh, and it flipped over. But let's zoom in and see what we've got going on here. And I don't know if anybody can tell me what is going on, because there's a whole bunch of stuff here, but does anybody see acceleration due to gravity on here?
Yes,
Where do you see it?
at the very bottom of the drop.
That's a big
I'm
number
sorry,
there.
That's 40.
That's -40. Is that it?
I hope not.
Let's think about all the things that went through when I drop something on the ground or on the bed. We've got a whole bunch of different motions that are being captured here. There's something else going on at the bottom of that thing. What was that?
The bounce.
It stopped.
That's probably the bounce. That's probably the stop. If I look at right before the bounce, we have some value right here, which it's a little low. I mean, I dropped it only once, and I probably didn't drop it directly straight down. It probably had some rotation in it, but that's that number right there. So in this particular case, my acceleration down, according to my phone and the way I'm holding it, is positive. I'm going to try that one more time and see if we can get another value. Again, we had a flop, and my phone actually flipped that time. So I dropped it with face down, basically. You can see the bounce all the way up at the top there, and down beneath it, right before the bounce, what do I get?
10.
Yeah, it's about -8.
9.
Yeah, -8. Yeah, well, whatever it should be, it's probably what it should be. But again, as some of you noted, it doesn't collect data instantaneously. So we may have also been capturing the data right before it actually hit the bed. It's hard to say.
Is there any way
so
to get
that's
the actual value of that acceleration?
Yes, there is. So on the phone here, we can't click and tap and get it, but what we can do, had I recorded it, which I did not do, but if you push that plus button and then pause, stop, you can actually export it, and it will export it as a CSV, and then you can email it to yourself, and then you could pull it into a data table and then actually find that. So I
That's
don't
nice.
think Pro allows you to click on it. I've asked my husband for that feature, but that's been a hard thing for him to get. So, but you could have lots of students collect data. All right, I am going to unspotlight myself again there, and I instead want to spotlight my screen share. There we go. And I'm going to share here. All right. So let's take a look at a couple other possible challenges. So this happens to be for my particular phone. The axis is negative to the left, the axis is positive to the right for the X, et cetera, et cetera. But this is one of the first activities I always have students do so that they can understand what the heck is going on, what is their frame of reference. And of course, our graph did not look nearly as clean as this, and it's possible that our data might have gone up to the top. So there's just a lot of opportunities for thinking about data analysis and zooming in on what is important and what makes sense in terms of measuring acceleration due to gravity. I would like to have.
Are you
Sorry?
sharing your phone? Are you sharing your phone screen right now? Because that's what we
No,
can see.
I'm sharing the slides. Are you not seeing the slides?
No,
Shoot.
we're seeing your
Chris,
phone.
Chris, are you able to, let me see here.
Yeah, let me see what I can do.
Because it says it's spotlighted.
Yeah,
I was seeing slides.
I was seeing slides too.
fascinating.
I don't know. Tell you what I'm going to do. I'm going to give you all access to these slides.
Let's try again.
Okay, I'm going to put them up because I want you all to take a minute and try a few different challenges. So let me actually share this link here. And I'm pasting it in the chat so you can all have access to my slides. And I'm going to go ahead and share my slides again and put this up. And I want to give you all a chance to choose one of the following. I'd like you to take a look at what does the force of a jump look like when you take off, when you move up in the air, when you move down in the air, and when you land. That's one choice. Oops, sorry. So you've got the slides on here. I don't want you to look at all the slides, I guess, but that's one thing that we could do. I guess we'll go ahead and not do that one, but this is a really, really, really effective activity for students. And actually, I would like you to go ahead and just do it right now. Go ahead and go to G-force and jump, and let's see what kinds of graphs we get. Take 5 minutes to do that. I'm gonna tell my daughter to stop playing the flute because she's making some noise that I'm sure you're all hearing. So take a moment and do that, please. Did people get anything meaningful? So typically when
I
my
got a
students-
double peak.
a double peak, awesome.
I
So,
made progress when I figured out how to pause it,
oh, good.
but I can change the time scale. But the vertical scale, I can't seem to change.
Let's see here. No, you cannot change the vertical scale. I'm sorry about
Okay.
that. Yeah. Some of these things are hard from a developer standpoint. But did anybody else get basically a double peak like this? Yep. So this naturally lends itself as an opportunity for when you're teaching about Newton's laws. And I would always have students then identify, what is going on at these different points in terms of the normal force on that person's body. So we can talk about net forces. And so when you're just sitting there, your G force generally reads really close to 1, right? And that's because the relative size of that normal force should be exactly the same value as the strength of gravity acting on your body at that point. The moment you take off while you're still touching the ground, what must be true about the normal force at that moment while you're taking off but still touching and pushing against the ground?
Go up.
It should be increased.
Yeah.
And that's also true of the landing. So that's why you get those 2 points there. While you're moving up in the air, how much is the normal force acting on your body?
0. Okay.
0. At least nothing from the ground, right? Maybe you got some buoyant force going on there, I guess, in this whole thing. But the ground is not pushing against you while you're moving up or while you're moving down. And this is extremely problematic for students to understand that at this point here to here, while you're touching 0, you are moving up and you're moving down.
Yeah.
If you want to get it even smoother, this is where I would have students take a smartphone into an elevator because you just get much more time extended data and all the kids can observe the same thing together. So that's one thing. The other thing that I like to do with students is to bring this in when I'm teaching about circular motion and centripetal acceleration, because again, students have so many misconceptions about these things. So I would love to have you try as well here. You could use normal force, although I think linear accelerometer is best if you happen to have linear accelerometer. And what I would like you to do is either to stand and spin with your arms held out nice and straight in front of you, and spin slow and spin fast, and see, number one, the direction of the acceleration, and see how the amount or the magnitude of that acceleration changes as you spin slow versus spin fast. So go ahead and take a moment and do that. And I always like to ask them too, spin the opposite direction. How does that change the acceleration? Or at least the centripetal acceleration. How did people do?
Is everyone still spinning?
Acceleration is positive in both cases. Either you
Yeah.
rotate clockwise or anti-clockwise. Maybe it
Yep.
is directed towards the center. That's the reason.
Yep. Yeah, absolutely. I mean, certainly there will be some initial like acceleration relative to the, you know, the left, the right, and the X axis, but nobody's gonna notice that. I don't think. Yeah. Beautiful. So this is an activity, of course, where I then have students draw what is the net direction of the force on the phone as you're spinning. So helps to reinforce to students that the centripetal force actually goes inward and not outward. I'd like you to try another thing, and actually for this, let me show my screen here. So sound waves is another thing that I love to bring smartphones in for. And I'm going to go ahead and share my camera. Can you spotlight my phone, please?
Yes.
Awesome.
Why can't I find your phone? Okay, there we
You have it? Okay, beautiful. So automatically you can see I've got an oscilloscope here. Is there anybody brave here who would like to make a really, really loud noise for me? And it can just be like, you know, a yell or, okay, I need to close the window. Hold on. So annoying that people decide to cut their grass. Does anybody want to make a loud noise?
Hello.
Beautiful. How about a quiet noise? Oh, quiet and then loud. And if we go, there you go. So let me see if I can make sure you can see the actual change in the thing, but I'm gonna go ahead and make a tune. So it's a little hard to see, but you should be able to tell that, you know, when it's really quiet, the amplitude is lower. I'm not sure if we're actually seeing that terribly well on here. Let me see if I can take a look at spectrum analyzer. Here's another way to visualize it. So kind of quiet noise and then very loud noise, and you'll see some peaks go up. But those are, yeah, it's a little harder to visualize on here. One thing we can certainly do is low tone and low frequency and high frequency. So, ooh. And I love having students just sing into that and take a look at the different timbre of everybody's voices. So that's super fun. The other thing that I like to do is to take a look at different beats. So I'm going to try to do a couple different things here. I'm going to take one phone and I'm going to turn on the tone generator. And I'm going to set it, I think a frequency of 440 will probably be fine. I'm going to turn on this other phone. And I am also going to turn on a frequency generator. And do any of you do this demonstration where you have two tuning forks that are exactly the same, and then you put like a little piece of clay on one to show beats?
Yes.
Yes.
Yeah, some of you do that.
Yep.
So let me go ahead and get this going here, because now a lot of times we'd always just take it for granted that the difference in those two tones result in the frequency of the beat. But if you want students to actually quantitatively figure out the difference, this is one way to do it. And by the way, you can tell there are some differences in these two phones. That's because I think one is an Android and one is an iOS. So don't be surprised when you see different styles, because it kind of all depends upon what students or what is standard for that device. So let me go ahead and let me actually see this 261 and see if you can hear it. Oops. See if I can turn up the audio on this thing. Can you all hear that clearly? Do you hear a noise? I need some
Did
feedback.
it
Yes.
first, but I can't hear it now.
No.
Okay. It's possible that Zoom's audio system might be making it a little hard. Let me see if I can take this up to 261 here. Oh, you know what I'm going to do? I'm going to actually do something different. I am going to change my video to be sharing screen. Oh, let's see here. No, let me not. Actually, give me 1 second. Let me try this one more time. So you need two devices for this. I'm not sure if you're going to be able to hear it or not. Oops. 1 second. So I've got two going on right now. I don't know if you can't hear it.
No, I think Zoom is filtering it out.
I can hear
Okay.
it now.
Oh,
Can
okay.
you
I can
hear the
hear it
beat?
now.
Can you hear the beat? Whoa, 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 whoa. Did you hear that? Let me try
It comes and
increasing.
goes. I mean, technically I can hear it, yes.
Yeah, I can hear a tone, but it's hard to hear the beats.
So here we effectively have no beats. And as I decrease this by 2 or 3, I'm hearing whoa, 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 whoa. It's very, very visible. And I'll tell you, if I had a third phone, I could have the oscilloscope right here, and we would be able to actually see those beats because of the, the superposition of the two waves. So if you ever can get 2 students or 3 students to do this together, it is quite powerful. And I think it could even be turned into a laboratory activity to measure the relationship between those two tones and then the beat that they end up producing. So that's that. Can you go ahead and refocus on my slides, please?
We are looking at your slides, or at least I am.
Oh, you are. Oh, okay. So I don't know if you were able to see what I was showing then, but okay. You're all seeing my slides now? Okay.
Yes.
All right. And then finally, another activity I like to do that is very, very effective is taking a look at magnetism and specifically taking a look at magnets to find out where the sensor is in the smartphone. And then this is where the use of a ruler can be really helpful. If you know exactly, or pretty close where that magnetometer is located, using that ceramic magnet you have, you could find out what is the relationship between the distance from the sensor and the strength of that magnetic field as you move away from it. And I think, as many of you know, you'll get a 1/cube of the distance relationship, which looks something like that. A lot of people do this with smartphones because it's just really, really hard for most people to get access to a magnetometer commercially. I know when I taught, I think I only had 2 of them, and even in our physics department, we didn't really have commercial magnetometers. Not for the whole class anyway. Light intensity is another one that you can do. This, of course, only will work on Android phones. And for this, I would use one phone's, like, depending upon what you want to do, you could use a point source, like another phone's flashlight, and then be in a completely dark room, pull your smartphone away and measure the light intensity, and you will get a beautiful 1/distance squared relationship. Another thing I'm not going to demonstrate because I can't make it totally and completely dark in here during the day, but your phone also has the capability of producing light. Some of you have a flashlight app probably built into the software when you got your phone the first time, but within Physics Toolbox, if you actually go to it under, let's see here, oh, it looks like iOS may not actually have it, but on Android, if you have an Android device, you should have something that actually produces light and can give off blue, green, red, and various combinations. And I like to do that for color mixing. And I'll often have students use their phones to project it over like M&Ms and then sort M&Ms under that monochromatic light. And that is one of the most fun activities that I have done with students. They just are totally blown away by the absorption of light. So I'm going to just pause here for a second. I am just curious to have us have a conversation. Do you see any opportunities or benefits for using smartphones in your classes, and what challenges or disadvantages do you see? So I'll stop sharing for now so that we can have a quick conversation. And I will just say, I've shown you kind of superficially what you can do, right? You can go really in depth with labs that you typically do just using smartphone sensors. And there will be some more things I'll be sharing with you in the next 25 minutes or so. Any reflections at this point?
Well, one
In
thing,
high school, oh,
I'm sorry,
go ahead.
please go ahead.
In high school, you might have to worry about them doing other things on the phone, talking to
Yeah.
their friends or whatever.
Yes, yeah, definitely. Some schools certainly won't allow smartphones, but most of the things that I've experienced, and let's see, sorry, Chris, can you spotlight me so it's not just showing my other phone? I would definitely say that most of the time I've found that physics teachers who want to use smartphones for an intentional purpose, administration will be supportive. But yeah, I mean, if kids can't handle themselves, I totally understand that. Nancy?
So I have a couple questions. One is on the G-force thing, isn't that measuring acceleration? So I'm just curious why you're saying it's measuring the normal when it, it's just measuring acceleration. I think, unless I have the wrong idea. And the other thing is, I was thinking of using it so students could play around outside of class, but if I want them to show what they did, how can I know you briefly I told somebody how they can get the data off, but if I want to give them an assignment, I want to see some evidence that they acquired some data and under what circumstances. How do they get the data off the phone that they can then, present in class or submit as an assignment?
Right. So to your first question about the normal force, so the normal force, I mean, I may botch this, but the way that I think about it colloquially is the normal force is, or sorry, the G force is, it is an indicator of acceleration. When G force is greater or less than 1, that's an indicator of acceleration with respect to your frame of reference.
So it's just the acceleration relative to G. So that's
it's not an acceleration. It is not an acceleration. It's basically telling you the relative value of the normal force, or the force basically opposing weight. I don't know if somebody has a better definition of it than that, but when the normal force is equal to 1, it means that the force opposing gravity is the same value as the weight, is the strength of gravity on that person, the force of gravity on that person. So yeah, it's a ratio. It's a ratio.
But the phone is actually measuring force, or is it measuring acceleration? So It's
So
just,
I'm gonna actually answer that question. Right now, we are going to watch a video. After I see if there's any other questions, we'll watch a video about how these things work, because you're right. This is not straightforward. And it actually works on a micro electromechanical principle that I think is fascinating, but students may not inherently understand. I like to think of it kind of like a spring. When the spring is stretched a certain amount, when it's a normal amount of stretch, for being not in motion, that is a normal force of 1. When it gets stretched or compressed beyond, outside of its normal circumstances, then it's a normal value of more or less than 1. So there should be in the app a little eye with a circle around it. If you click on it, it'll explain that.
okay, thank you.
Yep. And then for your other question, so honestly, Science Journal is one example of an app that does give a place for students to like report some of their data. For this, I'll be honest, most people still have students report their data using whatever traditional means they might use. So that could be a lab report, it could be creating a data set in Google Sheets or in Excel, making a graph, but doing some kind of data analysis with it. Some teachers I've known have students do video laboratory reports, things like that. But there is no reporting mechanism within the app.
I didn't mean that there was recording mechanism, but how do they get the data off the phone? So you make big taking data. How do you get the data? I know you quickly explained it to somebody else, but I was missing details. How exactly do they get the data off the phone?
So on most of the settings, there's a plus button. That plus button will start recording the data. So if you go to just GeForce and push plus and then push the stop button, it will give you the option to export that data to your email or to other apps that might be able to accept a CSV file.
Okay, that's pretty easy. Okay.
Yep.
Sorry.
Great. Any other reflections from anybody else before we move on?
I was going to say that, with the expense of lab equipment, if you are budget limited, as we all are in some way, it seems that, students with these ubiquitous phones, having the phone combined with software like this sort of takes the place of having to purchase potentially thousands of dollars of equipment.
Yes. I mean, yes. So as you've seen today in the past hour and a half, even I've gotten frustrated, by there's a lot of going back and forth between things. It's easier in person, I will say, but using new technology, using something that is outside the realm of what maybe teachers and students are familiar with has its frustrations. In some ways, it can also be very motivating for students, but yes, part of the reason why we developed what we developed for my students was because I wanted my students to collect accelerometer and barometer data on a roller coaster. And we had 300 some kids and we had 15 sets of equipment. Like that's just not going to cut it, right? From a day-to-day standpoint, I think if my students were used to using smartphones on a regular basis and use them appropriately and we're not getting distracted by text messages and all that kind of stuff, like I think you can develop a totally, completely awesome routine where maybe you don't need those other things, but there's a few things your phone's never going to do. Your phone is never going to do a force meter, like from like a proper force meter. I'm not talking about normal force. I'm talking about like Pasco and Vernier have legit force meters, right? They have things like force plates. The stuff that they've developed is highly precise and more so than that, it's like super appropriate to specific labs. Some phones are never going to cut it, and most phones will never cut it for certain labs that we just don't have sensors for. So I agree and I disagree in that sense that there's just going to be limitations. So.
Has anybody used these in the space station?
Not on the space station, but they have on the training parabolic. They call it the Vomit Comet. Sometimes they send educators up to go do like quote unquote zero G experiences, but not the space station, I believe. That would be cool. All right. let me share a couple other things with you because they're the really good question from Nancy about what the heck and how is the accelerometer actually working and what is it really measuring. I'm going to disconnect my regular phone. So give me a second. I'm going to go on mute and unmute myself from my computer.
All right, can you hear me okay from my computer now?
Yes.
Okay, great. Let me see here. I am going to share my screen and we're going to watch a quick video about how these micro electromechanical sensors work. So let me share my screen, share sound, share. And okay. We'll go ahead and see if I can get this started. Let me know if you don't hear any audio, okay?
The accelerometer, it measures acceleration by measuring change in capacitance. Its microstructure looks something like this. It has a mass attached to a spring, which is confined to move along one direction and fixed outer plates. So when an acceleration in the particular direction will be applied, the mass will move and the capacitance between the plates and the mass will change. This change in capacitance will be measured, processed, and it will correspond to a particular acceleration value. Next is the gyroscope, which measures.
But I'll just pause there real quick and say, so that's what's actually happening mechanically inside of the phone. So Nancy, to answer your question, so this thing is like on a spring, right? And when it's exactly positioned in the middle, it knows that it's not tilted, it's not being accelerated because there are basically no additional forces on those springs.
But how does it
The moment it
factor
starts
out
to
the
move,
G-force?
things start to happen. Sorry, question?
Yeah, wouldn't it also just detect the force of gravity?
Yes, it will, which is why technically some of you have a G-force meter only, but don't have an accelerometer. So every phone will have a G-force meter. The accelerometer actually requires the use of a gyroscope. And so there is data, there's some kind of data, some kind of a process that I don't fully understand, to be completely honest, and may not even be open to developers. So while we call things an accelerometer, it's really a G-force meter that gives G-force data. And that's how your phone knows up from down, you know, like so that your phone can rotate the screen and things like that. And so for some lower end phones, and some phones just simply don't have a gyroscope, you're not gonna be able to get linear acceleration. Linear acceleration will take into consideration actual like rotations and things like that.
So it magically takes out the G-force.
Yes, effectively, it basically takes out the G-force. That's correct. So here's another video that will give you a little bit more insight. And I think it's about 4 minutes, but I think it's worth the watch because it's so foundational. And it gives another model example. You're hearing it okay, yes?
I think this is one of the coolest features of today's smartphones. It knows up from down. Built into the circuitry is a tiny device that can detect changes in orientation and tell the screen to rotate. Now, let me show you what it looks like using an old iPhone. There it is. It's an accelerometer. I'll tell you how this kind of chip works and how it's made, but first some basics of accelerometers. They have two fundamental parts: a housing attached to the object whose acceleration we want to measure, and a mass that, while tethered to the housing, can still move. Here it's a spring with a heavy metal ball. If we move the housing up, the ball lags behind, stretching the spring. If we measure how much that spring stretches, we can calculate the force of gravity. You can easily see that 3 of these could determine the orientations of a 3-dimensional object. Well, lying with the z-axis perpendicular to gravity, only the ball on the x-axis spring shows extension. Turn this on its side so that the z-axis points up and only the accelerometer along the spring on that axis stretches. So how does this phone and this chip measure changes in gravity? Well, more complex than the simple ball and spring model, it has the same fundamental elements. Inside the chip, engineers have created a tiny accelerometer out of silicon. It has, of course, a housing that's fixed to the phone and a comb-like section that can move back and forth. That's the seismic mass equivalent to the ball. The spring in this case is the flexibility of the thin silicon tethering it to the housing. Now, clearly, if we can measure the motion of this central section, we can detect changes in orientation. To see how that's done, examine 3 of the fingers on the accelerometer. The 3 fingers make up a differential capacitor. That means that if the center section moves, then current will flow. Engineers correlate the amount of flowing current to acceleration. This accelerometer fascinates me, but even more amazing is how they make such a thing. It would seem nearly impossible to make such an intricate device as this tiny smartphone accelerometer. At only 500 microns across, no tiny tools could craft such a thing. Instead, engineers use some unique chemical properties of silicon to etch the accelerometer's fingers in H-shaped sections. Now, to get an idea of how they do this, let me show you how to make a single cantilevered beam, like a diving board, in a small chunk of silicon. Empirically, engineers notice...
Pause it there because you'll have access to these slides and can watch some additional information about it. But does that now answer the questions about what's actually going on? I hope.
Yeah, I knew that, but that it's really just it's not okay. So maybe we're just talking you know, it's language, but I always teach that the normal is the component of the surface of a contact force is perpendicular to the surface. And for them to then it depends, I guess, on how you teach it. So I teach normal in a very specific way. And so this doesn't match with how I teach it, but essentially they're measuring the acceleration just using an inertial accelerometer, which I do teach in my class about inertial accelerometers, but I think this is great. This is a better explanation than I give, so I might I might adapt it. So thank you.
So actually the actual chip is called the IMU, the inertial mass unit, I believe. That's exactly what it is. It's basically an inertial mass kind of a thing, but it's doing so, of course, using a capacitor, right? Now, gyroscopes are more complex, but if you understand the ideas we just saw, a gyroscope is not that complicated. But we're going to quickly take a look at physically what's going on inside of. I think this is showing the gyroscope here. Let me move this up. Minute number 1 for you, real quick. Sorry about that.
When a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this. A mass that is constantly moving or oscillating, and when an external angular rate will be applied, a flexible part of the mass would move and make the perpendicular displacement. Okay, now let's explain.
So I know that was like super fast, but basically you've got a capacitor sitting inside of another capacitor. Some of you may have seen, there's a really cool YouTube video, I don't think I have here, of 2 kids like rotating. They're like, spinning around on a bar, and they're throwing a ball to each other to demonstrate the quote unquote Coriolis forces. That's basically what it's sensing, is the Coriolis forces. There's another quick video here, I think it's like 10 seconds, which just gives another beautiful, not quite 10 seconds, but I will speed it up.
Sensor is installed close to the vehicle's center of gravity, in the airbag ECU, for example. The yaw rate sensor comprises 2 comb-like structures linked by a spring. Each area comprises 3 nested frames, connected with each other by springs. An alternating current makes the drive frame, red, oscillate. If the vehicle drives straight ahead, the detection frame, blue, remains in a resting state. During operation, the 2 frames oscillate in phase opposition in order to avoid false measurements. If the vehicle changes direction, the Coriolis force deflects parts of the comb-like structure, which move the deflection frame. The capacitance between the comb-like structures changes in proportion to the speed of rotation.
There you have it. So there's your gyroscope, which again, not all phones are going to have, but that information is necessary to get the linear acceleration data, which basically cleans up the gyroscope, the G-force sensor, data to give you true quote unquote true acceleration data. And I would say in general, I don't like black boxes. I don't like it when kids have like literally no clue what's going on. So I often use, just like if you've ever taken students or have seen students at amusement parks carrying around springs, using a spring is just a perfect, simple model for them to understand what's happening inside. And then we've got magnetometers. I'm going to show you just one more final little clip because I will tell you there is not a lot of information out there. And I don't know if this is all like stuff that you already knew, but I feel like I, as a physics educator, really had no clue about this. And I have scoured and have not found good resources other than the videos I've shown you here. If you have other resources, I'd love to know, but I didn't have the background. So I'm just going to quickly show you the magnetometer and how that works, which uses a similar electrical principle. So I'm going to that one quick moment.
Hello, then it looks perpendicular displacement. Okay, now let's explain how the magnetometer works. It measures the Earth magnetic field by using Hall effect or magnetoresistive effect. Actually, almost 90% of the sensors on the market use the Hall effect, and here's how it works. If we have a conductive plate like this and we set current to flow through it, the electrons would flow straight from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow and the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means that if we put a meter now between these two sides, we will get some voltage which depends from the magnetic field strength and its direction. The other 10% of the sensors on the market use the magnetoresistive effect. These sensors use materials that are sensitive to magnetic field, usually composed of iron and nickel. So when these materials are exposed to magnetic field, they change their resistance. Okay, now let's connect these sensors to the Arduino.
All right, so that's all I think I'm going to share with you about how these things work. There is another video about barometers. Long story short, a lot of this stuff is all semiconductor science, and depending upon how those materials are deflected, how their conductivity or resistance changes, or their capacitance changes, that's how all these things are measured. So you can take a look at those on your own time. And then I do have a lesson in here that, again, so much I think of using this technology as building familiarity with it. And some of my frustration with myself is I don't use it all that much, to be honest. So I feel like I fumble a lot. People who get used to doing this kind of stuff with their students do not fumble quite as much. But one activity that I think is really, really good with smartphones, if you have the barometer sensor, is measuring height with pressure. Because if you do this activity, students will see a negative linear relationship, which is fairly unique among physical principles, I think, that we touch on in introductory physics. We often see inverse relationships. But basically, this is me collecting measurements at different heights and seeing that, the higher I go, the lower the pressure. And what's beautiful about this is that if you know the, is basically you're able to get the density of the air, which I think is super duper cool. You can do the same experiment as well underwater. So even with a single bathtub, if you take one of those water protection covers for your smartphone, make sure that there's a little bit of air inside of it. You can dunk it in the water and measure the distance under the water and the pressure, or even have students go to the swimming pool. So I think about these as kind of like great opportunities for just getting kids out there doing other things. I've also had students take a look at projectile motion by taping the phone and the accelerometer to their chest or their abdomen and going to dance class and jumping, right? As they're doing their, whatever they call their long jumps or whatever, in dance class or in sports or whatnot. So it just gives students a lot more capability of grabbing data from the environment. And before we go, I want to show you two more things. One of which should work on everybody's phone if your phone is like 5 years old or younger. And it's called Magna AR. And it is something that I've never seen done with any other technology. So this uses AR to visualize magnetic fields. So I'm going to stop my share here and I'm going to reconnect my phone. And for the rest of you, as I do this, if you would go into the app and then go into magnetism and then Magna AR. And I'd like you to look through the tutorial and see what you can visualize in terms of the Earth's magnetic field. I'm gonna go on mute for a second and reconnect from my phone.
Awesome. Okay, so if you go to magnetism, we're going to go to Magna AR, and this is a feature that, like I said, is something that I've never seen anywhere else, and is something that a lot of students really struggle with. So I know we've been very much jumping all around all different kinds of topics in physics to give you a broad survey. Could I get a thumbs up from people if you've been able to access Magna AR? Either virtual or real. So Rajasree's got it, which is good. Good. Larry did not. Larry, you may not have Magna AR. Maria's got it. Dean's got it. R. Baker's got it, I think. Prabhat's got it. Okay. So I'm so sorry if some of you don't have it. For this, again, this is a hardware kind of a thing. So it's not the app, it's the hardware. But many students will have it. So first thing, I know you're seeing my keyboard and my hand and whatnot here, but one thing that you'll notice, 43 microteslas. Does that ring a bell for anybody? What that is?
Earth's gravity?
It is not quite Earth's gravity, but it certainly is related to
Sorry,
the Earth.
magnets.
That's all right. I figured that's what you meant. So that's the Earth's magnetic field right there. And you're seeing this is one of the rooms in our house. One thing that you can do is tap a button and you will start to see, or you should start to see, some vectors. Could I get some verbal feedback from people? Is anybody seeing vectors?
Yes.
As they tap? Other people as well? Okay. That right there, my friends, is those are vectors that represent the Earth's magnetic field at that point. Does this strike people as interesting, unusual? What do you notice? What are you thinking as you see these field vectors?
That it indicates the direction of the Earth's magnetic field at your location.
Absolutely. And I told you I am in Washington, D.C., where the Earth's magnetic field may come as a surprise to some people, but I believe it's 55 to 60 degrees from the horizontal. Does that look about right?
Yes.
Yes. Now, what do you think most students actually would have expected to see?
90.
Most people would expect to see it horizontal, pointing quote unquote towards the horizon, because they all think we're flat on a flat Earth, right? So the thing that's nice is you can go to the side and take a look at these from different directions, and you can definitely see there is a direction. It's kind of pointing down this way. This general direction here is north, but the North Pole, or which is the South Magnetic Pole, is not straight ahead of me in a flat sense, right? It is actually definitely way down, because we know that the Earth is curved, and also so are those field lines. Those field lines don't follow, they don't go parallel to the surface of the Earth. So that's a big surprise to people. Now, the other thing I can do is I'm going to go ahead and grab some magnets. And there was a question earlier, and yes, I know we only have 9 minutes left, but this is something you can play with later on your own time. One of the things we can do is take these magnets and we can plot the field as we get close to it. Keeping in mind that, so, as I get closer and closer, you'll see that that magnetic field value increases. I can also place some arrows And you'll notice that what kind of an end is this, north or south? That would be a south pole because my magnets, my field lines must go from, hold on, they go from north to south, right?
Yes.
So that's a north right there. So I'm hoping, I'm going to hold this in the same place. I'm going to go underneath it and capture some data there. And I'm hoping that those arrows actually point towards the bottom, which would be the south magnetic pole. Let me see if I can pull away, see if I captured them. Oh, I did. And as you can tell, I didn't do a super perfect job, but you can definitely tell that those arrows right there are going more towards it than away. Anyway, folks, sorry?
When you tap on the screen, at what distance does the phone put the vectors?
Great question. So in order so your phone is putting the vector on the screen where the sensor is actually sensing it. So if I'm all the way back here and I put a vector right here, that vector is pretty much just Earth's magnetic field. If I get super duper close, you know, with that 1/3 squared law or whatever, I probably have to be within 10 to 15 centimeters in order for it to be collecting data that's actually sensible.
Got it. Thanks.
Yeah, you have to play with it for sure. And I also want you to know when you get too close, sometimes it will tell you that it, let's see, these magnets aren't very strong. Sometimes it will tell you that you have to reset your phone. If you ever end up magnetizing your phone and you don't go back to the appropriate amount, like you'll see here, I'm at 104 microteslas. I'm going to spin it around in a 3-dimensional figure 8. And somehow magically, through some kind of an algorithm that probably only Google knows, it resets it back to around where it was in the mid 40s or approximately. So sometimes you have to recalibrate your phone. So that's one thing. That's one thing for you to play with. There's one other feature that I want to share with you, but I'm only going to share the website. Let me go ahead and could you go back to featuring me on the computer?
Yes.
Thank you. And I'm going to go ahead and try to leave Zoom on this other one. All right, I'm back on my computer now. So the other thing that I wanted to share with you, which is only available for iPhone, is called LiDAR. Let me go ahead and share Chrome here real quick. Actually, I'll just show you on the slides and I'll provide the links to you afterwards. But this, by the way, for Magnet AR, what we were just looking at, you can get data that is big and beautiful, just like this in a 3-dimensional format. You've got to take your time with it though. You've got to have a strong magnet and you've got to have a lot of patience. But it is absolutely possible to get visualizations like that. And it certainly beats using iron filings. So there's a whole bunch of stuff you can do with that, which we're not going to go into today. And then the other thing I wanted to share with you is this thing called LiDAR. Let me go past this, sorry. LiDAR is another tool that uses something that's only available on iOS. LiDAR motion visualizer basically uses iPhone Pro's accessible, they've got multiple cameras. It sends out an infrared ray beam and then it waits for it to come back. So it's like the proximeter, except that it works up to about 8 to 10 meters, which means it is a motion detector. So as we were talking about like Vernier and Pasco and TI and all, you know, the other great companies that are out there, many of them have sonic rangers that go click, 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 click. And I love those. They're super effective. However, if you happen to have kids who have a whole bunch of iPhone Pros and you don't have those sonic rangers, LiDAR motion allows students to match their motion
to specific graphs, and then to build conceptual understanding about what does it mean to have a line that has a small slope, a large slope, a negative slope. What does acceleration look like on a graph? And they use their bodies to walk back and forth. So I know we're basically out of time. I'm gonna share a couple different things in the chat while we're closing up here, and then I'm happy to stick around for any questions. So the first thing I'm gonna leave you all with in the chat is the slides for you to explore. The other thing I'm going to leave you with is the website for Vera Software, which has a whole bunch more resources on it. And then within that, we also have a page that's dedicated to Magna AR. Let me see here. So I'm going to put that. This is the magnetic thing that we looked at. And then specifically for LiDAR, because that's an active NSF grant, we have a special dedicated website for that. So that's for the motion visualizer. So anyway, I hope you've had a chance to play around with the smartphone and at least build a little bit more comfort. Probably none of us have the expertise that would be like make things totally and completely smooth in a classroom, but I hope you're willing to take some risks because the benefits, I think, are definitely they can be great, especially especially in light of lack of resources and things like that. And kids love using their own phones. So Chris has a feedback form that she needs you to fill out, and I'm happy to stick around for any questions or further discussion. And thank you so much for your time.
Thank you so much, Rebecca.
Thank you. Thanks.
Thank you.